I don't think we are recording now, so that's okay. So I will share my screen. Okay, can everybody see my screen? Can you hear me? Oh, okay, cool. Okay, thanks guys. So, okay, today we're gonna see how we can design a femur implant and perform a finite element analysis on it for some loading scenarios. So just we will repeat what is our problem, and we will do a very brief recap of what we did in the first workshop, as this is a continuation essentially. So the idea was that a doctor wants to perform a partial hip replacement procedure. Partial hip replacement procedure is when you replace the femur bone, the top of the femur bone, essentially the ball. You mount it into the existing femur bone, and you just perform the surgery because you have some wear on the ball, but you do not change the socket. So it's just the ball. And we were asked to design and study femur implant. So in the previous workshop, let's say, we got a 3D CT scan from a patient where we were able to isolate the sections, the cross section which included the bone. We were able to distinguish the bone from the muscle tissue and the veins and all the associated stuff. And the difficult part was to distinguish the bone, the ball of the bone, from the pelvis, because it's essentially a ball and a socket, and the boundary between the ball and the socket, sometimes it's hard to distinguish. So we were able to distinguish that and extract a 3D model of the femur bone, of the top part essentially of the femur bone. Then we used another program to fix some meshing issues or some imperfections that may be present in the model and make it smoother as it should be. So that's how we end up with a 3D model, with a pretty accurate 3D model of the patient's femur bone. For this workshop, our goal is to design a very basic femur implant that could be used as a replacement to the top of the femur bone of the patient. So just to go over the steps, the first step is we will need to measure from our 3D generated model on the previous step, we will need to measure some critical dimensions in order to know how our patient bone is, what are the critical dimensions, and how the implant will fit. On the second part, we will use these dimensions to design a femur implant. We will design a rather simplistic femur implant, not a very detailed one. Then we will go into choosing a suitable material and deciding on some scenarios where we can evaluate implant's performance, essentially how it's going to be used in a daily life. What our patient is going to do with this femur implant, how long he's going to stand, if he's going to run, if he's going to walk, if he's going to jump or whatever. And finally, we're going to perform a finite element analysis for the different scenarios we decided. And just see if there's a problem, if the implant can hold, if it can't, if it needs any improvements. Usually, if you had a project like that in a more real life scenario, especially these steps you will iterate again and again until you get a solution that is sufficiently good. Okay, we're not gonna do that, but it's good to know. So first off, let's see how we can design a 3D model of the hip implant. Obviously, we can use the design as it was extracted from the CT scan, But that's not very helpful because on the one hand, that's a rather complicated geometric shape, and not all the details of this 3D model contribute to our cause. So we need to stand out, we need to check what are the details that really stand out. Also, just in case you need to study this or have a similar project, when you're dealing with a common problem such as hip replacement surgeries, it's a really good idea as you're working on the problem to search online for resources. For example, for hip replacement, there are many cuts online. There are products that are in the market right now. There are a lot of literature, papers, so you don't need to reinvent the wheel. Just keep that in mind. As you're working on a project, keep searching online, keep looking out for resources. Don't just copy paste things, but try to understand and reverse engineer why someone did design something the way he did. Just a generic guideline. So back to our problem. As I said, we generated the 3D model in the previous step. And now, since we have it in an STL format, it's easy for us to measure some dimensions and see how it looks. So the first part is that's a general semantic representation, of the femur bone. You might have the right or the left, it doesn't make any difference. So we will need to measure the diameter of the ball, since that is critical because it has to fit inside the socket. If we make it too small, then we will have a lot of play and it won't fit perfectly. It won't be a good fit. If it's too large, again, we will have a problem because it won't fit inside the socket. That's the first dimension. The second dimension that we need to measure is the dimension BC, and generally define this axis. It's called the femoral neck axis. The reason for that is because this angle is very important in order to fit, and also this length. Okay, guys, so we know how much offset we have from, let's say, the axis of the femur bone to the end of the ball or to the center of the ball. You can measure whatever you want. So taking these three essentially dimensions, we can just create a very simple sketch. You can see it here. It's not a big deal, okay? And starting to build from that sketch and steadily adding dimensions and stuff like that, we can create a very simple 3D model that will allow us to study the problem and see problematic areas or some insights to better understand it. So that are the dimensions you will need to measure. We will look this into detail afterwards in SolidWorks, so I will show you how you can create the 3D model. Also, guys, are you familiar with SolidWorks or you use some other 3D CAD? Have you been taught anything? Or
Κυρίως
it's
SolidWorks χρησιμοποιούμε.
SolidWorks, okay, το ξέρετε, δηλαδή, you're
Ναι, ναι, ναι,
comfortable.
ναι.
Cool, that's nice. No, we will be using that as well. If someone is not comfortable with SolidWorks and needs to work on another program, it's perfectly fine. That's not a problem. Okay, go ahead and work whatever fits for you, whatever works best. I'm just using SolidWorks because I mainly use it for a ton of things. So we will see this in detail afterwards. Then we will need to study the model, this basic geometry we created. We need to study it and see if it's good for our purpose, if it can serve as an implant or not. So one of the first steps is to select a suitable material. Now, when you're dealing with a highly regulated industry and some very challenging and specific applications that can be implants, you can't, it's not a good idea to just go out there and start looking at materials because there is only a handful of materials that are suitable to be implanted in a patient for an extended period of time. So you have to keep that in mind. There's a relevant ISO also for that, and many other standards such as DIN, ASM, and stuff like that. So for example, usually for implants and for implantable materials, some very common materials are stainless steel. Not all stainless steel, there are specific grades, of course, but also some titanium alloys are very common. And PTFE is also a very common solution. PTFE, you might have heard it as Teflon. Teflon is a trade name, but PTFE is, okay, the material's name. So keep that in mind when you're dealing, especially with medical devices. You can't use everything you want because there are a lot of toxicology studies in order to prove that the material is suitable to be implanted. That is pretty difficult and it's pretty expensive, so you just can't go around searching for materials. It's better to narrow it down from the beginning. So the second thing we would like to see are the mechanical properties of the materials. Uh, in this case, guys, and usually when you have the early stages of a project, it's usually helpful to have an understanding of the properties of the material. So as to be quick to get a ballpark figure of what yield strength you're looking at, what young modulus you're looking at. So again, you can narrow down the materials pretty fast. So for this example, we will talk later about more for it, but let's say we will use a titanium material. This is a specific grade, and that's a typical data set. I've singled out a couple of values, that is the tensile strength, the yield, and the modulus of elasticity, because that's what's interesting for us, at least for this application. So moving on, just a quick recap of material properties. I'm sure you all gone through this just in case you need to refresh them. Stress against essentially force per cross-sectional area, and we use stress and strain in order to make things dimensionless. And the stress-strain curve is the simplest way to describe the mechanical properties of the material. So this is not so typical stress and strain curve, but you can see a lot of things on it. This first region that is linear, it's the elastic region. The slope of this line essentially is the Young modulus or elastic modulus. When you reach the end of the elastic region and go into the plastic deformation, you have the yield strength. And moving on, you have the ultimate strength, which is the biggest stress a material can withstand, and you have the fracture. Now bear in mind, because this is not for a specific material, it's kind of a weird diagram. When we're talking for metals, especially titanium, for example, you're gonna see a curve that's more like this, since metals do not tend to deform, they kind of form a lot like, rubber or plastics, so their curves are a bit different. Since now we're talking about an implant, we don't want it to go into the plastic deformation stage. That's not acceptable because it's going to be used for extended periods of time. It's going to be inside the patient. So you want to stay well within the elastic region area, okay? So just to get an idea of how the stress strain curves looks for this titanium alloy, this is pretty much a straight line, and we're interested in this first part, okay? And this, the A part, is the yield strength, or as we saw above, it's approximately 880 megapascal. So I hope you remember all this. Now we have a material and we have an idea about the material properties and what we're looking for, what is crucial and what is important for us. We have to think a bit about the scenarios and the use cases, how it's going to be used, how this implant is going to be used. what are the loading that it has to withstand in the daily life. So some very common, use cases and simple, it's, for example, walking. Obviously, we walk a lot during the day, so this is probably more of a static loading, and it will need to withstand at least the body weight of a person. And if we go into a bit more detail and thinking, we can start thinking that walking is not the worst case scenario. You can have someone running, you can have someone jumping, where the loads might very well exceed the body weight, and we need to withstand the higher force. Also, when you're talking about medical devices implanted, because usually when you insert an implant into a patient's body, it will stay there for quite a significant amount of time. Usually, you're looking at least 5 years or something. You also have to wonder how many stresses in a daily life this will be subject to. For example, we might be very well off and very well in the elastic region for several kilos or several hundred kilos, for example, for our implant. But what happens if we have this loading, but in many cycles, we have this loading over and over again, and that are things you have to consider. And based on these use cases you have and the worst case scenarios you have, or what an average day perhaps looks like for a person, for example, how many steps do we take, how fast do we walk, do we work out, all these have to go into consideration when designing this implant. And this might seem overwhelming, and it is difficult to create a handful of sets from all these parameters. But again, as I said earlier, when you're studying a pretty common problem, and femur implants are very common, you can find a lot of resources online. So, for example, just for femur implants alone is ISO 7206, and you can see a long list of ISOs of that pretty much define what are the measures and the metrics of success of an implant or of the failure, what loads it has to withstand, what are the geometries it pretty much has to cover, how you can test it. So right now, because it's a very common problem, we can pretty much skip this step. We don't need to think this all for ourselves, and we can just perhaps download the ISO, read them through, and decide on the experiments we need to do. Also, something to consider is because you're dealing with medical devices, a medical device, before it can be used, it needs to be certified. Certified means that a regulatory or a notified body, an organization anyway, will come and audit you and check your files and the experiments you perform on your medical devices. And in such cases, it's a very good idea to follow very well-known standards, because they feel comfortable that your product, your design fits, your design will not fail. So have it in mind. On the one hand, you don't need to think and design everything from scratch. On the other, it's much easier to get this certified CE mark for your implant and have it on the market. So, as I said, just some very basic tests, that you need to consider with the femur implant. First, it's static loading. Okay, that's a very basic requirement. It's an easy to study. A bit more challenging, and you'll figure out why, is fatigue limit. The fatigue limit is the stress level below which a pretty much infinite, let's say, number of loading cycles can be applied to a material without causing fatigue failure. And looking back to the dataset of this alloy, you can see, for example, that although the tensile strength is a pretty big number and we might feel reassured for static loading, if you go here below to the fatigue strength, you might figure out that is a lot lower than the yield. So if you have repeatedly load the implant, even with a much lower force, you might cause it to crack or fail, and that's something to be very wary of, especially when you're talking medical devices. It's something that has to work for many years, so we have to take that into consideration. Something else you might want to look into is, for example, the friction between the ball and the socket. Essentially, we have a metal part or a ceramic part or whatever coatings we have, and this part is rubbing against the bone. So that's also some considerations. You need to think about, will it cause damage to the bone? Will the metal might be damaged from the bone? It might cause pain to the patient. It might feel uncomfortable because the friction coefficient is pretty high. So again, going back to the ISO standards for hip implants are very specific, and you can find a lot of information there. For example, this is a device that is used to test femur implants. The implant is placed under specific geometry. It's fixed with a specific way here. And for example, for this test, a maximum load of 2.3 kilonewton was selected, and the run-out cycles were set to 5 million. So just to give you some idea of what happens is they completely control the conditions in here, the temperature, aeration, what is the fluid test medium in here, and they have a load of up to 2.3 kilonewtons applied uh, up for 5 million cycles. And if your implant passes this test, then you're pretty sure that it can withstand the loads of everyday life. Uh, and also, guys, the ISOs go into a lot of detail, especially for such things that are really common. For example, you have determination of endurance properties of stem femoral components. You have endurance performance of stem with application of torsion. So if you encounter a problem where there are ISO standards, do use them. Sometimes they can be very detailed and they can be really helpful for you. So summing up, once we have our design, in order to test that our design complies with the standards and it's safe to use for a patient, there are three steps mainly, and for medical devices and generally, the first step is called in silico. Sometimes essentially our simulation. In our case, it's just finite element analysis. Then you usually move into in vitro testing. You move into in vitro. In vitro is usually tested in laboratory environment. In our case, it was this machine just applying loads again and again to our implant, so we can check that everything is okay, it can withstand. And usually the last stage for medical devices is in vivo. That means real testing in human patients or in animals, depending now on the medical device, on how risky it is. There are several stages. Usually you go first to animals, then you go to humans. And an interesting fact actually is that for high risk class medical devices, that means the devices that have a high risk for the patient, sometimes just this third step, the clinical trials, where you need to prove that your medical device is safe and is efficient and can be used humans, is one of the most costly stages of the entire development. And usually all the steps before that, the development, the design, is just a fraction of the clinical trials, especially when we're talking, okay, class 3 risk class 3 medical devices. Yeah, so just something to keep in mind. For that, you may see startups, raising tens of millions of dollars just to go into the clinical trial phase. So this is pretty much what we will be looking at today for your homework, and we will see it together now in SolidWorks. We will just create this 3D model out of taking some dimensions. We will create, I'm sorry, wrong slide. We will, where is it? Okay. We will create this 3D model, and then we will apply static loading to it in order to see how it behaves, what are the critical areas, what we need to be wary of. And I'm going to be using SolidWorks for that. Obviously, you're free to use any program you want. There are many programs out there, both for finite element and for design. SolidWorks is usually better for designing. It's not that good for finite element analysis. ANSYS is usually, when you want to be accurate and correct, it's better for this part. But today I'll be showing it in SolidWorks, but you can do it in whatever you want. And also, just a heads up, guys, after you extract these dimensions from your own model, I will give you the dimensions to go from this to this, okay? I will give you 2D design, so don't worry now. I'm just going to show you the process. You don't need to write everything down. I will provide it with the presentation, okay, after the class is over. So give me just a second to move my other screen because I don't have SolidWorks installed in this computer. Okay, guys, can you see the SolidWorks screen now? Hopefully you can.
We can.
Okay, cool. Uh, just give me a sec. Okay, so this is the 3D model we're going to create. Obviously, it's a pretty simplistic model. There's not much to it, but it's a good starting point to start and studying and see what trends we have with this particular implant. If you have any questions regarding the design, I will design it now for you and we'll see the finite element analysis and all these things. Just interrupt me, ask me whatever you want, okay? Because, okay, there are some technical aspects to SolidWorks. It's not hard, but it can save you a lot of time. Okay, so let's start from scratch. Okay, so first things first, in order to give you a better idea of what we're making, I'm gonna sketch the basic geometry here, and I'm not gonna use it to extrude just yet or create a solid out of it. I'm just gonna create it so you have a better idea of what I'm doing. Also, in general, it's pretty helpful to use SolidWorks and especially 2D if you want to study the kinematics of something, how it can move, put constraints and stuff like that. At least I find it very useful. So I'm just gonna use center lines for now. I hope you know what center lines are. Essentially, you can't extrude solid from center lines. They're just, let's say, lines to assist you when drawing, okay? So let's make the basic sketch in the beginning. Okay, I hope you know that, but a very helpful feature is to put a relationship between the different lines and points. So for example, if I choose this point here, I press the control key, you probably can see that, and I choose the line. I have this menu here and I can choose coincident. So make sure that this point is coincident with this line and this line can move along on this point, okay? Now I'm gonna put some dimensions. These are indicative, but they're not actually dimensions. They might be a bit different from your 3D model, but it's okay. Don't worry about that. So I'm just gonna put this 98. This is also a very important angle that you have to take from your 3D model, okay? And now for me, suit it's something like 120 degrees. Make sure you're working with degrees and millimeters also. Okay, now I'm gonna specify this length to be 120. That's a bit arbitrary. It's not extracted from the 3D model in any way. So let's make the ball as well. Again, now I want the center of the circle to be coincident with this line. So you click on the one, you press control, you click on the other, you get this, you put coincident. Now this circle can move along this line, okay? It's constrained, it can move only along this line. And because of the geometry we have, I can pick this point, I can pick the circumference of the circle, and I'll say coincident. Okay, so I'll also make this for construction. If you click for construction, it just makes it so you can't get a solid out of it. It's not a big deal. So, okay, one thing to know, you probably know it, but for me it was useful. So when you see everything black in SolidWorks, that means your entire sketch is fully defined. Okay, and you don't have, you can't move anything. So that's helpful because sometimes things can move around in sketches if you haven't defined them, and this can be really tricky. So we have this basic, very basic sketch. You see these are the critical geometries, dimensions rather, we got from our 3D model. So we'll start working on this sketch and try to create a 3D model out of it. The 3D model that I'm gonna create is not so much accurate, but there are several simplifications inside, so it's not really a big deal for you to design it. I think you can design it pretty easily. But if you have any problems, again, do say so, okay, guys? Uh, so, but I will provide you with a detailed 2D design, guys, okay? So we will just make a really rough outline now. And now I'm going to start putting some dimensions here. Again, these are not dimensions that are entirely based on the 3D model. Some of these are just simplifications to make the exercise a bit easier to do. And that's why the 3D model is pretty simplistic. Okay. Oh, sorry. Now, for example, okay, that's my bad, guys. Sorry, I just aligned this with this. Yeah, I made it coincident, and that's a mistake. Sorry. Is it here? Okay. Okay, so what happened? Okay, now, for instance, this line shouldn't be vertical. That's why it's giving me all this message. I just delete that and make this a bit here so it can stand out. Sometimes you can get automatic relations in SolidWorks Sketch, and it can be pretty tricky, but just make sure you delete anything you don't need. Okay. So I'm just sketching an axis line here to help me. It's not a critical part of the design. Just a minute, guys. I think I did some. Okay, something is wrong here. I need to figure out what it is. Okay. Okay. Okay, so now we have a fully defined sketch. Don't pay attention to the dimensions. I will provide it to you. It's not exactly parametrical, a fully parametric design, but you just need to begin with this simple 2D design, and the rest will it will come up as you work. So, okay, this is the design essentially we're trying to make. The first solid we're gonna create is the sphere. So we go ahead and begin a new sketch. Now I have the sketch visible, but another way to do it is just you can choose the circle, for example, and click convert entities if you just want to see it in your sketch. Okay, for now it's not required. So the way to create a sphere, you probably know that, is you just revolve half a circle around itself. Okay, again, now make sure you don't leave any gaps here because SolidWorks can be tricky with very little gaps. If you leave some very tiny gaps, it might say that it can't extrude the boss or create a solid out of it because there are gaps, and it's really annoying sometimes. So make sure the points and the end points are all correct. Okay, so I'll make this concentric, I'll make this coradial, and I will merge these points. I will merge these points again. So we exit the sketch. We select the sketch, we go to revolve boss plate, and hopefully we won't have. Here it asks us to ask axis of revolution. For us, this is the axis of revolution. And by this cross section, by revoluting around this axis, it's able to create a sphere. Okay. Now something to keep in mind when you're working with spheres, it's sometimes it can be tricky to attach a handle or something to a sphere, because if that was, for example, a flat surface and this is a sphere, they essentially share just one point. Okay, so to tackle that, there are a number of solutions. I'm going to show you the most simple one, actually. Also, a good practice, if you're sharing your designs, is to rename them. For example, instead leaving revolve, we can say that this is the ball, or the femur ball, or whatever. So when a new designer comes in, or when you're looking your designs after a long time, you can pretty much remember what is which. And now again in sketch, we're gonna make the handle, let's say, or the rest of the bone. Again, go to the front plane, sketch. Let's bring it vertically. And now again, if in order not to design all these things again, you can just choose these lines. Okay. You can say convert entities, so it brings it to your sketch. So even if I hide the sketch, for example, now I still have these lines in my sketch, which is pretty helpful. And now I will convert these lines for construction, and I will explain you why. If I just connected these lines here, then I will end up with a very weird looking solid, because there will be gaps between this surface of the solid and the sphere. In order to make sure there are no gaps, I'm just gonna go and extend these lines to go well into the sphere. Okay, so now I have a closed shape. I'm gonna make this to collinear. I'm also gonna make this to collinear. So now I don't really care about that because we're gonna trim it afterwards because it interferes with the sphere. But for the moment, let's just give it a dimension so it can be, it's not poorly defined, you know. We can say, for example, it's 5%. Okay, and you need to give it an angle as well for some reason. Okay, so okay, it doesn't matter. These dimensions don't matter. You will see now why. So now we have a closed shape and we can extrude it. Make sure, because that is essentially in the middle of the sphere, when you try to extrude it, make sure you choose here from the mid plane. So if I have a thickness, for example, of 6 millimeters, let's say, okay, then it extrudes 3 millimeters from the one side of the plane and 3 millimeters from the other. If you choose blind, it goes all the way up and then it's off center on the sphere. I'm not sure if you can see it correctly, but that's the idea. So one is also important feature here, keep this merge result. If you don't keep this merge result, if you don't take it and you do this, then you end up with two intersecting bodies. You can easily correct this by using just, you know, in case you need it, if you use the combine feature. Okay, but it's much simpler to just go here, edit the feature, and say merge the results. And if I merge the result, you can see that this body now no longer interferes with the sphere. And at the same time, it comes in contact throughout this. I don't have any, let's say, blank spots or whatever that are gonna cause an issue during the meshing process later. Also here, you can go ahead if you want and just put some chamfers and fillets around here, okay? Now 10 millimeters is a really big one, let's say half a millimeter or something. And these are not mandatory, guys. It's clear, purely optional. If you want, you do it. If you don't do it, okay? But just so you know, you can add, or you can add perhaps a fillet here or whatever. Now, in order to mimic a bit the ISO, we're not gonna leave all the stem. The stem is intended to go deep into the femur bone, on the existing femur bone. So we're gonna create again a sketch, plane sketch. Okay, so, and we're gonna cut it at 80 millimeters from the center of the sphere. So I will just convert this entity so I can work with it easier. Now I have the center of the sphere and I can say that I need this to be 80 millimeters. And you can add also some dimensions here. Again, they're not critical. It's just to have a defined sketch and not have things floating around in your design. Okay. And I need to define this. Yeah, to test this. Okay, that's now fully defined, and we're just gonna cut it. We're not gonna do anything more to it, so it's just an extruded cut. You go here, you go through all both, so you completely cut it. Okay, you don't leave anything, and you end up with this model that we're gonna use for the finite element analysis. In SolidWorks, since I'm showing in SolidWorks, you just go here, you click edit material, hopefully it won't lag too much. Okay, it's lagging, sorry guys. Mhm. Okay, sorry about that. Okay. And because it doesn't respond, sorry, I'm gonna open it again. Save it. Okay, guys, because it didn't actually save it, that was my mistake. I should have saved it in between. I'm just gonna open the previous model. It's the same. Just gonna open this so we can move forward. Okay, now we have this. For this particular, I did assign it a material. It's titanium alloy. I will tell you what material to assign it in your assignment. It's okay. So go to SolidWorks add-in. We're going to be using SolidWorks simulation, which also usually takes a decent amount to load. So hopefully it will be okay. Also, something to note, one reason we're not using the 3D models you created from the CT scan to perform finite element analysis is that usually because they have imperfections and the meshing is pretty complicated because there are many different surfaces, difficult model, and it takes a lot of time and a lot of processing power for these programs to analyze the stresses and the strains on such a model. When you do a simpler geometrical model that, you know, that are flat faces, this is just a sphere, it's usually a lot faster. But, you know, if you want to use your own model, you can go ahead, but bear in mind it will take a lot of time to load and to analyze it, because the meshing is much more complicated. Okay, how does that works? Okay, so it loaded. So you now go to SolidWorks simulation. Sorry, let me maximize this. You go to new study. Now you can choose several studies. You will choose here static. Okay, so it's static study. For me, static too, because I already have one. So this is okay. Now what you're gonna do first is add fixtures, because this needs to be stabilized somehow. So it's fixed geometry. You go here, you select the surface. Okay. Fixed geometry is πάκτος στα ελληνικά. Okay, it can't move. Okay, essentially. So this is okay. This is the constraint we have, because when you're performing a finite element analysis, you need to have a constraint and you need force or something else. Okay. Now we are also going to apply external load. We're going to have a force. Now, also something to keep in mind, having concentrated forces, it's not very realistic. So we're gonna use this now. Just put select direction here so it's not normal. And now you need to select the direction, just select the vertical direction. It goes up, okay, then just click reverse direction. Here you can put the force in Newton. This can be, for example, 700 Newton approximately for someone who is 70 kilograms. And that's pretty much it. Now we have the force, we have the constraints. Because SolidWorks is a more user-friendly software, you don't control a lot of the parameters. It does this for you. So then you can just click run the study. And if I did everything correctly and I didn't mess up the geometry, it should run pretty well, okay? And pretty fast actually. So you end up with these results. This is the stress according to von Mises stresses. You probably know this already. Also, in case you overcome the yield strength, you see here there's an arrow, it will appear here. You can change the scale here and stuff like that. And you can see with the color diagrams what are the most critical areas. For example, here is this for this design. Okay. You can also see the displacement. Where is the displacement larger, where it's smaller. Okay, that makes sense because here we have a fixed geometry, we have fixed it, and this is free, so displacement should be larger here. That makes sense, okay? And you also have the strain. And that's an easy way to study static loading. But what you can also check is for materials like titanium alloys that have a very specific fatigue strength. You can check here if the fatigue strength of the material, if the stress, rather the maximum stress is above or below the fatigue stress of the material. So for example, here for one loading, it will definitely have no problem. As we can see, we're not even close to the yield strength of this material, but for repeated loadings for 5 million cycles, it's interesting to see if it can withstand or if it can't. So this is pretty much it. This, what we saw now with the SolidWorks, is gonna be your homework for next time. And I'm just stop sharing for now, guys. And I'm gonna open the laptop again. Okay, this. So again, guys, sorry, just sharing my screen again. Okay, so this is gonna be your homework for the next time. You're gonna produce the 3D model. You can extract the critical dimensions from your 3D model from the previous assignment. You're gonna use this to design a new 3D model. I will provide you with a material dataset and what material to choose. If you're using SolidWorks, I will make sure that the material properties are pretty close to already provided material, so you don't need to define every property from scratch. And you will need to, the deliverable will be on the one hand the 3D model, and on the other hand you will need to perform the finite element analysis. I'm not sure if you want to ask anything, if you have any questions, or if it's okay with you, if you understand what we did today. Everything okay, guys?
I think ready. Can tackle it.
Maybe? Or you're sure?
Okay, I'm sure. I'm sure.
No, no, it's okay. It's okay, guys. I don't know how well you know SolidWorks here, or perhaps you know these things a lot better than me. Perhaps you don't. I'm not sure. Just ask me if you want anything. Okay. We're not trying to put too much work for you at this stage because you're ending your studies, so you pretty much know the theory behind it. It's just using some tools. Okay. So you understood what we did with a model, how we created the 3D model. That was clear. I don't mean the dimensions. You don't need to remember, obviously, all this. We'll send it to you. I will provide you with 2D design and you will transfer them. I just wanted to make sure that you understood what we did. Okay.
Yeah, I think it was pretty easy.
Okay. Okay, guys. Since we said that we will talk with Mr. Alexopoulos afterwards, you can probably take 5-10 minutes off. Okay. We will resume then. I will just call Mr. Alexopoulos and okay. See you in 5 minutes. So take a break. And we will be back. I will also stop recording for now. Γεια σας.
Okay.
Μόλις τους έλεγα να κάνουν 5 λεπτά διάλειμμα.
Ναι.
So,
Οπότε 1
okay.
και 10 ακριβώς. Είναι 1 και 6. 1,
Ναι.
10.
Okay, I
10
stop sharing guys and I also stop the recording. Το σταματάμε το recording ή you want to keep it?
πάτα, όχι pause, stop, τελείως.
Oh, okay.